so aren't entirely sure how to wrap stuff up, so feel free to send me email. Will probably give a quick response, maybe not kind of super detailed at this point, but I can guide you on questions. Is it better to do this or that sort of stuff? Also my office hours tomorrow, I need to fill in for a lecture for someone. So I'll be in the computational topology class until about 10:30. So my office hours won't start until then. If you have questions, you had really been planning to come and see me in my office hours then, let me know and maybe we can find some other time. Okay, and then the last homework has been posted. So it's on the stuff on the topic now on graphs, and so you should basically be able to get started on it. It was mainly kind of most of the kind of technical stuff turns out was in the lecture on Monday, and there'll be some stuff that was in the lecture today as well. There might be some kind of some review of some elements also on Monday the 15th, but you can get started on it. It should be due so let's do it in 2 weeks. Because there's no class this day, I let the deadline be 5 p.m. instead of 2:45. But you should. So hopefully that's enough time. It should not be too hard to do. MATLAB will make it very easy to do it if you do it in MATLAB. And the bonus question is worth 5 points, and it's not meant to be as hard as some of the other ones. So if you feel like you might be a little bit below a threshold for score, this is a good opportunity to kind of try and make up some points. And then the final report will be due on Monday, and I'll actually bring in some posters then because your poster outline will be due the Wednesday after that. And so if we can worry more about that after you do to finish the final report.
So speaking of poster outline, what exactly are you expecting us to do?
So I hope you produce like a draft of a poster.
Can we just on the regular people, or should we already?
Yeah. So you should you will turn in a PDF through Canvas. So the final poster that will be printed will print posters for you, and you'll turn a PDF into Canvas, and once we okay it and everything, we'll print it. Those will need to be done the morning of April 22nd. That's just the amount of leeway we need to get them all printed by Thursday. There's something like 50 posters, right? So I anticipate.
So basically just the way for you to give us feedback on our designs, on how we design it.
So most of the posters we'll get feedback on because they won't be up to my standards. So this will be one of the things. You are given 15% of your project grade. I think something 10 or 15% is based on completing the poster, and I will give you feedback on it. I'm not going to kind of take off points if it's like if I need to give you some more feedback, but you should give an initial draft by Wednesday the 17th. Okay, and then we will start giving feedback, and the final version needs to be completed, I think 9 a.m. Monday morning was the deadline I was given in order to get them all printed by Thursday. All right, so you'll need to they'll be back and forth, and we'll give you, and hopefully your final version, you can keep uploading new versions into Canvas, and then at some point we'll say, okay, we've taken that version and sent it off to be printed, and they all need to be done by Monday morning on April 22nd. Okay, but I want the first draft in by this Wednesday. Okay. So, and hopefully that first draft is, as close as your kind of, don't make it be garbage on the first draft, right? So put some effort into it by then, but you can say, okay, I'm going to refine it, and then when you say, okay, this is the final draft, and we'll say, okay, we accept it, or you need to make these changes, that needs to be done by this date in the morning. Okay, great. So, and we can talk more about posters on next week, Monday as well. I'll give you some feedback on that. There's some written in the project description. So if you read that, you'll see all the details. And you might want to reload that in your cache if you haven't done that in a while. Okay, so we're going to talk about the PageRank algorithm today, which is, and this has kind of been, and more really on the kind of the history and the place of PageRank within search engines. And this is, and we'll see why this is kind of part of the section on graphs, because we can kind of model the web as like a large graph as we see. So, but I want to start by saying kind of, so how does a search engine, like how does it work, right? So what's your, so have you like learned about search engines in any of your previous courses? Yeah? So like which course?
So in linear algebra, my professor on the last day passed out the Pagerank algorithm paper and read us all.
Oh, okay, cool. Well, so that's part of how a search engine works, right? So PageRank we'll see is like an element of it, and it will relate back to linear algebra, as you're aware, but the rest of you will see this. But like, you think of a search engine as you type in a keyword into Google, and almost immediately these lists of web pages pop up, right? And PageRank will be an element of that, but that doesn't really tell you how a search engine works, right? How do you quickly get all these lists of web pages? So PageRank will be used to kind of score which web pages are better, but how do you quickly get this list?
Google cache on all of the web pages based on like a bunch of different keywords and whether or not like people clicked on it and then back out and click on another one, or whether they clicked on that one and didn't go back to the search one.
Yeah, but so like, I mean, this is a little, when I first learned about it, it was kind of unintuitive too, but you're still not saying, it can't kind of go and do computation to score all the web pages every time I type in a different keyword.
There's like a worm that crawls through all the links and then builds caches based on the information that's on the links that it crawls through.
Yeah, so the key part I want to first mention is this cache, right? So there's this data structure called an inverted index. Okay, and basically what this is this kind of, it's a list of all of these, all of possible like these keywords you might search for, you know, so like you could search for each of these words, and this is this massive list which has been pre-computed, and for each word it has this list of like these pages, right? So for each of these words, you know, it has these lists pre-computed, right? And so this seems like a lot of space, but it turns out there aren't too many different keywords people actually search for. Okay, so they pre-compute as many of these as they can, and if you search for something like apple and pie, so apple space pie, it will take both of these lists and try and pick out kind of the pages which are in the top part of both of these lists, right? And so if you search, your web page actually only preloads up to, say, the first 10 of these pages, right? So it really only needs, it's got a long list of all the words associated with the word apple, and it can look these up. And so if you keep saying, show me more results, it'll keep going down this list. But it'll only preload the first 10, and in fact, your browser probably only shows on the first thing, the first 3. So it really only needs to preload the first 3 that you can see, and it can wait until you scroll down to see the first 10 off, right? So it really has in a very fast cache the first 10, and then someplace else it has stored the ones kind of going down. So if you keep clicking on like more results. So like back in the day, with search engines were becoming kind of coming online. If you remember, you probably were more likely to search for something and have to keep going further and further down the list. Okay, nowadays, I rarely look past the first page. And it's because search engines have gone better, right? And there's a variety of ways they've gone better. And I often kind of click on. I don't even scroll down most of the time. I'd say, in my experience, 70% of the time I don't scroll down, and 99% of the time I don't go past the first page, right? It's probably might be even higher than that, right? So it really needs to kind of pre-order these pages for each of these keywords. And so if you search for something where there's like a misspelling, let's say I typed in apple I'm missing one of the P's. Usually it will do something like it will use something like the edit distance to say, well, this is really close to the word apple, and here's some web pages for the word apple, right? If there's a very obvious misspelling there, but it will, even maybe this is a not too strange combination of letters that they might actually have pre-computed kind of page even for this. Maybe it's a code in some like stock market index or something like that. This might have its own, like predefined list of pages. All right, so this inverted index is pre-computed ahead of time, and this is how it works so quickly, because it's pre-computed as much as it can. Okay, and we'll talk a little bit on next week, Monday, in how it does some of this pre-computation, because it has to do this for lots of pages, and if you update kind of how you list these things, you want to update these things, and it does this at least once a day. I think probably more often than that now. It used to be they would redo it once a week or very early on, and then it was every night they would recompute this index. Now I think it's probably even like more dynamic, especially with stuff that's in breaking news. They try and want that to happen, be going on all the time. This is kind of the structure that makes things go super fast. But what's really important, the reason that these are so effective is the order, okay, and especially the front part of the order. Okay, so which web pages are the most relevant for searching for a keyword like apple or pie or data or something like that? Okay. So most of what we'll talk about today is how do we come up with this order, and PageRank will play a role in this, but there's actually kind of a longer and I think worth like revisiting history of this. So pre-PageRank. So this would be, say, about, well, it's just, this would be like, so like pre-1998 or 1996 is around when this was invented. So how did we do search on the web, right? So there were these companies that like predated Google. There was like Alta Vista. Got a list here. There was like Lycos, like InfoSeek, right? It's like how do these search engines work? So this simple thing behind them was that the idea was for each web page, I would look at the HTML text, and I would do like a bag of words vector. And so doing like shingling was also involved. So I think Alta Vista focused on shingling. I think others use like the bag of words. And maybe it could be a combination of these things. So it would convert these into a bag of words. So a page, some web page I would go to a vector I in some high dimensional but very sparse vector in some like maybe 10,000 dimensional space, right? And so VI might be 0, 0, and then if it has the word apple on it, it's going to have the word 8. If that occurs 8 times, and then if it has, the word pie has an index, and this occurs, so like 5 times. And so if there's a web page that's about apple pie, then it would have other words in here too, but the words apple and pie would be in this bag of words vector for this web page. And then if you search for the word say apple pie, then you would have a query vector, which would also be in our 10,000, which would be so maybe this one would look like 1/2 at the word apple, or this would be 1 over square root of 2 if I normalized it, right? So I would have a query where I would query with the word apple and the word pie, and this would be normalized. And then I would ask it against all these existing bag of words vectors for web pages, and the ones that have the highest similarity would be the ones that would be the first ones ranked. Okay, so then the highest, so let's see, the highest cosine similarity between VI and Q would go to the top of the list. All right, so this is kind of, and so around this time, these ideas of like locality sensitive hashing were formed to do either cosine similarity or like using Jacquard similarity using the, so like the min hash was like invented in the context of like Alta Vista search engine for doing searching and deduplication of web pages. And so so we could do this fairly quickly, and we could pre-compute this like inverted index. Okay. So this was kind of how things worked, but this was not like super effective. So, and as soon as these search engines came aboard and a lot of people started using them, people who were like creating their own web pages, I created my own web page my first time around this time. I wanted it to show up in the search engines. So you would try and do things that would make it show up like in the search engine based on the keywords. What's something I could do if I was a search engine and I wanted to promote my recipe of like apple pie? So when someone searched for apple pie, it would show up at the top of the list. You could pay them. Alta Vista, Lycos, and InfoSeek, I don't think they were doing that too much back then. That was some issue, but that was not the, I mean, you can do that now more than I think you did then with these guys. You
could just write apple pie like a million times at the bottom of your web page, and then like use CSS to change it so that didn't appear to users, but the like web crawler would see that and give you really high dimensions in other areas.
Yes, this was pre-CSS, but you know, like for better or worse, they still have the thing following your cursor around and all that other nonsense. But pretty similar. You would write apple pie, apple pie, and just write this over and over again, and write it so it's in white, or the background of your page may not have been white back then. So as long as it's the same as the background of your page, then you know. So then you couldn't see it, make the font really small, but you're right, the search engine, which is looking at the HTML text, would still see it, right? So HTML is this really kind of language that allows for errors, so you couldn't really, it was, you know, you could write it in a way that it appeared in white, but the search engine parser might not know that it appeared in white, even if you tried to do that. Right, so you put this super small over and over again at the top of the page. It would inflate the terms in this vector, and it's going to look just like this query. Right, so then this query will return it to be very high similarity. Right, so this was kind of happening. So there was kind of this battle between these search engines. So versus these, it's like spammers. Okay, so these you know, even just regular people, or there are companies that could try and get your web page elevated in these search engines, and they would help you do these tricks. And so this was kind of this was kind of like a back and forth, and so. There was like the search engines would do something like they would modify the like the distance, right? So it could be something like the average of cosine distance and the like Jacquard distance, or it could only you know, emphasize. So it could do something like emphasize like certain words, or it could like cap the like the word count, right? So that if you said apple more than 10 times, you stop counting, right? You know, so you can't do something like that. Or if you search for apple pie, the query vector, you could do something like the query would not just be apple and pie, you know, right? But it would also give some of the weight to some other similar words. Like if the word recipe is on there, it would know that people searching for apples might search for recipe, or there might be other words. They would modify the query in some way. So it's not as peaked at certain words. It'd be more susceptible, and they would keep this a secret, right? And still to this day, Google does not say how exactly their ranking function works. They keep some aspects of this a secret, so you don't know exactly what words to copy. Okay?
Could this be that they take into account the semantics of what you're searching for? For example, if you have an apple pie search without the word recipe, it understands that most likely you're going to be searching for the recipe and give you recipes rather than just giving a definition of what apple pie is, for example.
Yeah, so I don't know exactly how they do it today. They keep it a secret, but I imagine they use something like these word vector embeddings, where they look at the word apple and the word pie and these word vector embeddings and look at the nearby words there, and those should be the words which are like this like the synonyms. And then if it has lots of those words, then that will show up in some sort of query vector like this, right? So it'll try and do something like that, and that would be an automated way of doing that. Back in 1995, this sort of technology was much more premature, and they may have done something like it, but not as advanced. I'm guessing Google has been very involved in the development of these word vector embeddings, so I'm guessing that's one of the key uses they use it for. So there are these things that like a search engine could do. I could play with how this works, kind of play with the distance, not totally say, and so you couldn't spoof it quite as easily, but there was kind of another fairly obvious trick that spammers could do that would allow them to still get on top of these like search engines. So there's some set of words probably in a query and some weighting of them defined by how I define this distance function. I don't know what it is, but you do know which web pages are ranked on the top, right? So what you can do is you can go and search for the keywords you want to be you want to be associated with. Look at the top web pages and paste those into the bottom of the page in small font in text that's white, right? So what you do is you copy top pages into bottom of like your page, right? So I can search for them in the search engines. It tells me what has been effective, and I copy that. And so you can imagine this back and forth. As they update this, they go and play this trick again. And so there's kind of, and there are other tricks as well, but this is kind of the one that kind of was giving the spammers like some sort of an upper hand here. The people who made an effort to do this without having necessarily better content could get their pages elevated. There was too much stuff. These companies did not try and hand curate what was going on, so they had to have a completely automated way of doing this, right? So I've heard stories of like Andre Broder, who was one of the kind of key engineers at like Alta Vista, and has gone on to do other great stuff. Like he was one of the inventors of like the min hash. At some point, there are things like he was tuning the algorithms like every day to try and speed the efficiency with new stuff coming online and to beat these spammers. And like it was like going on for a long time where he was kind of personally battling both the scale and these sort of effects. So at this time or so, there were a couple other things that was going on. One of there was these competing ideas to these search engines, right? It was not clear that search engines were the right way to build a way to interact with the web. The more traditional thing was the thing we had that was closest to the web pre-web was like the phone book. And if you remember the phone book, you searched by something in the phone book because it was alphabetical by last name. So if you only knew the first name, you're kind of out of luck. But by the last name, and it's just this big index, this big list, right? And everyone had a phone number, which is kind of like a pointer. It said, can we build something like a like a phone book on the web? And so there were these other kind of objects that were referred to as like an index that they started by, these people started just curating the web and collecting all of these links. And so there were two kind of well-known companies, so like Yahoo and so LookSmart, right? So if you don't know the story of Yahoo, there were two. This will sound like familiar later if you know PageRank, but there were two PhD students at Stanford who spent a lot of time on the web and just started collecting a bunch of links to cool web pages. And at some point, they realized they were getting so much traffic on their web page that they started a company. So this became Yahoo. Okay, they just collected links to web pages and they tried to curate these into categories. And so they, spend a lot of time personally kind of browsing and hiring people to browse in certain categories and trying to keep updates to the most interesting pages. And so like the business model here was these kind of paid placement, right? So these were very successful companies, kind of even when there wasn't nearly as much funding in the web as there is now, but certain web pages could be paid to be placed inside at the top of some category, right? And they built these big empires. So Look Smart, I don't think is around anymore. Yahoo is still around. Does anyone use Yahoo anymore?
Yahoo Finance mostly.
Yeah, yes. Okay, so it turns out that Yahoo is still one of the top 10 most visited websites. Actually on the internet. A couple of years ago, I had it ranked at 4 or 6, and I looked this up just today. And if you look at a top 10 list, Yahoo is around 9, or there's another ranking. These are from Wikipedia. So it's the 9th most frequented web page based on some website, some company's estimate of the number of page views, the numbers of like distinct users. They're kind of, it's fishy how they measure it, but if you measure it that way, it's like number 6 still. It's still an enormous business that has evolved out of this, and kind of this index model kind of eventually failed, but it was not clear at all back in the mid-90s. Yahoo was as dominant as these search engines, and was more effective because of these spammers, right? They could just curate web pages that didn't make sense. They could take them down, right? They couldn't automate as much stuff, but they hired a bunch of people to go and do this. And imagine being paid to surf the web all day. So I won't comment on that, but it was not as pleasant back then. Remember, you had dial-up modems, and so maybe it'd be fun to kind of see if you guys can guess which are the other top web pages. So nowadays, based on kind of, I took this off like Wikipedia today. So what do you think is the most popular web page? Yeah, so the top one is Google, and this is based like a factor of 2 more than any other web page. And then number 2, Wikipedia is further down. Wikipedia is here. So what was the other guess? Yeah. So YouTube is number 2. So Facebook is number 3. And Facebook and YouTube are pretty close. And then there's a big drop after that. What do you think is number 4? Reddit is, it didn't even show up on any. It was pretty far down.
Twitter.
So Twitter is like 11. By one measure, it's 7 by the other.
Instagram.
So to hear Baidu? Yeah, so number 4 is Baidu. So Baidu was also actually founded at the same time as Google with a very similar algorithm. Turns out, but that's the top search engine and related stuff in China, if you don't know. Other guesses?
I was saying Instagram.
Instagram, I think is, let's see. By the second measure, Instagram is 10. Yeah.
Amazon.
So Amazon is 10, or by the other measure is like 11. Netflix is the most popular by the total amount of traffic it sends, right? The amount of content it clogs up the web. But by these measures of distinct page views, it's much lower. That's like 23 or 17 would be Netflix.
Weibo.
So Weibo, I think is in the. I didn't write it down. I think it's in like the teens. What? Bing is not in the top 10 in either ranking.
Alibaba.
So Alibaba, you're starting to get good guesses. It turns out Alibaba is not, unless it's one of these other things I don't know is
eBay.
so eBay. No,
Not anymore, I guess.
yeah.
It's not like a bank
So no, I didn't see any banking. So think like Baidu is in China.
Oh, you're talking about some other countries, not the United States.
So I'll give you the next one from China. So the top 5 are pretty clear. Those are all the top 5 in both rankings. After this, so Tencent QQ, which is also is like a Chinese version of Yahoo. It's like a portal that has lots of stuff. 7 and 8 are also from China. Tao, so Bao, and so Tmall. Both of these are like shopping in China. Okay, so those I think those have pushed Yahoo down the last couple of years. So okay, any other thing? And there's also like a Yandex search engine in Russia. Yeah, that's like number 9 on the other ranking. So okay, yeah. So these are kind of the top things. Google and probably YouTube and Baidu and Yahoo are all based on like doing search, right? That's their primary thing. YouTube is really search for videos, right? So okay, so this model of Yahoo was like fairly different, right? We're going to completely curate the whole thing. But you know, with PageRank, which I'll describe soon, there was this other way of thinking about it, and one of the other components is this idea of like these crawlers, and this is like so this is like an automated bot that that kind of moves around the web, right? So it's crawling the web. So think of it like a spider or a crawler or something. And so what it does, it'll visit a web page. And in order to build these search engines automatically, they would visit the web page, capture all the information, do whatever, kind of pre-process it for cosine similarity or something else, do shingling maybe, and then it would click a random link or do like a depth first search, and kind of follow a link on the web page, and then moves to the next web page and keep doing this, right? And so they would automatically discover content by walking around the web. And so this is how they would automate this, and this is still how it works to kind of discover new like this new content. Google will also know that certain web pages refresh more regularly, and will just know to revisit them every day or every week to kind of update like their indexes. Right? It might notice that the DayMine web page is updated roughly twice a week. Every week I post these notes up there, so it probably knows that it should actually go and check to see if anything remarkably new has been posted, you know, every so often. Or it might notice that it's not a big change, so it doesn't check back that quickly. But like a newspaper, it'll check very often. But these crawlers would just kind of crawl around the web, and they would follow links, right? The idea is to follow these these links, and so the first kind of the idea of like an innovation is that if I'm collecting information about a web page, right? So I have this page here I'm interested about, and it has this information, but I get to it from the crawler. The crawler is going to follow this link, then it can also gain information from what is in this link. Okay, so there's usually a piece of hypertext, you know, that you click the highlighted word and that sends you to the other page, right? So the text in this hypertext turns out to be pretty informative, right? So another big innovation was I could use this text. If someone said, here's a great recipe for apple pie in this hypertext, right? Right in here, then that's actually a really good, kind of a recommendation of this page here, right? So if I can take this information and build that into the representation in the LSH, whatever my search engine, my search structure is for this web page, then that's even more effective. I can't just do this page. I need to have other pages which are linking to it. Right, so search engines started to kind of gather their data this way, and this was this was informative. This helped combat against spammers. Right, so, but if you were a spammer and you were trying to create your web page to be ranked high in the search engine query, how could you, almost like how could you kind of get this page to be ranked high?
You could just create a bunch of web pages that said here's a great apple pie recipe that links to your web page.
Yeah, right. So I can create all these copies of these other web pages, and they all have the same link with the same hypertext. And so I'd have to create these other web pages, but it turns out it's not that hard to do that, right? So if you're hiring a company to do this, the company can create all these web pages for you. If you ask all your friends to link to your web page, then back in the 90s, having kind of a few handfuls of links to your web page with the same hypertext gave a very strong signal. Right, and so if you wanted the web page for your own personal web page with your name, you would have your friends link with your name in there, and then you'd create this kind of graph. And this was pretty kind of informative for these these search engines. In some cases, it was effective. In other cases, it could still be spoofed. There became this larger industry. You didn't just modify what was on the page, but you did this external stuff on the web that caused this to happen. Right, and so these web pages didn't need to have anything on them. They just need to have the hyperlink. They just need to exist. They need to be found by search engines. So, there need to be something else here that would link to all these web pages so they could be found by the crawler, right? Right, so the crawler would find these and then go onto your page. Okay. So so this was kind of the state of the art, still pre-PageRank. What PageRank had the idea that not only did I want the hyperlink to be meaningful, but that so the PageRank idea was that web pages link to important web pages. Okay, so I didn't just want to be linked by some random web page, but I want to be linked from an important web page, right? So if I'm kind of like the president of the University of Utah, like Ruth Watkins, she will be linked off of kind of one of the main page for the University of Utah, possibly, right? The page that she probably doesn't maintain herself, but is kind of maintained for her. Then they'll link to that, and that'll be more of a direct signal that she's an important person at the university, right? Whereas mine's probably slightly further down. You have to go through a few pages until you find mine. So this seems kind of like this is okay, but there's like this like chicken and egg problem, right? Where how do I know which of the web pages are going to be important, right? And so this is like the first idea. The second idea is that important web pages are so visited often by a random surfer. So right, so if I'm kind of bored and I start browsing the web, and I do this by clicking on a web page, and then I click on the next web page and the next web page, and I just kind of randomly like click links. I'm kind of randomly surfing around the web. And so this is kind of modeled by the crawler. You know, so if I have the crawler randomly clicks links on a page, each page is equally likely to be, each link is equally likely to be clicked, then I'm kind of randomly walking around the web. And if a crawler is going to hit my web page often, it's probably more important. Okay, so this gives a different sense of importance that I can actually measure based on this crawler. Right? And if I'm running these crawlers, I gather this information, right? I just count how many times does it come on this web page. Okay? And this kind of fits with the first idea, it turns out, because important web pages are the ones hit by the crawler, and then if they're there, they're more likely to jump to another important web page, right? Because if the crawler's on the first one, it's more likely to get jumped to because it was the first one a lot, and so forth. Hopefully you kind of see where this is going. So I can model the entire web as a as a graph G, right? And so the vertices are the pages, and the edges are the hyperlinks, right? So the edges are the hyperlinks in between the pages, and the vertices are the pages. Okay, and so then I can define this graph of like the web, and then a random surfer. This is then a Markov chain on going around on the graph, right? So either, and so this random surfer way of counting is this random walk model where I'm walking from one page to the next, and then I keep track of how many times I fall on each web page. But we also know that I can set this up as a graph, compute the adjacency matrix, and like find the first eigenvector, or compute it with these power method and these other techniques as well, right? So I can use eigenanalysis now to give an importance of the web, and so basically the first eigenvector then is what's called, or almost, there's a couple more things we have to do, but so from the web graph G, I can create an adjacency so matrix A. Then I can turn this into a probability so transition so matrix P, and so then the V1 equals the eigenvalue, the first eigenvalue of P is going to be defined as the PageRank vector. Okay, and so we'll call this a function R, and so each function, each page is going to have a PageRank score, and so the larger the better, right? And so this tells me this page is important. So now I can kind of, my So I'm going to have some score of some page, and I'll use which is going to be so given a query like apple pie, for each page I'm going to have a score, and this is going to be some magical combination of the PageRank score, the cosine of the cosine similarity of the page, and the query vector, and some other factors, and it's like the hyperlinks. Okay, and so I can now fold all of this in, but kind of adding in this, so the score, and then I rank the ones based on, I pre-compute this inverted index, and the ones with the highest score for a certain query word are going to be the ones listed on the top. Okay, and so adding this PageRank score into here was a really important piece of this puzzle. So this is so the PageRank score right here. So this was kind of a very important way of like thinking about this and pulling this in. And basically, the larger this, the more higher ranked it was going to be. Maybe it's going to be adding up components from all these, or multiplying them. It's not clear exactly what they're doing, but it involves all these different factors. Okay. This is part of the answer, but we're not quite done yet. So is the web graph ergodic? Right? So remember this ergodic we defined on Monday. It was this nice property the graph needed to have, the markup chain needed to have, in order for me to be able to apply to eigenanalysis or to use kind of the power method to compute in order to compute a score that it actually converges to. Right? Otherwise, it might not converge to the score. Is the web graph actually, is it actually going to be ergodic? Okay, so first, there are three things. So does this have cycles? So the answer for this is no. Basically, as long as any one page has a link to itself, has a self loop, then it won't have cycles. Okay, so we don't need to worry about cycle elements. Is the graph so connected? Okay, so it turns out it's not connected either. There are web pages that I don't, I can create a web page and I have some that I don't link to, but I can still use them to share information with other people. So it doesn't necessarily need to be actually connected. That's not such a big deal. You can index the part of the web which is connected, the crawlable part of the web. So this is probably okay. Okay, but does it have these transient nodes, right? If you remember, if I have this part of the graph here, which is well connected to itself, but if I have some node over here, and if once I get to this node, I can't get back. Remember, this one is like the Hotel California. Once I get to it from the graph, I can't get back to the rest of the graph. And the answer is yes, it has had pages like this, which means this part is transient, which means a random walk will always lead to here. These are web pages that might not have any links to them, right? So they might not have any outgoing links, right? They have no outgoing links, right? If you have no outgoing links, it doesn't link to anything else, right? So at some point, my dad made a web page, but he didn't know how to make hyperlinks. So his web page didn't have any links, but I linked to it, and I made the whole. So I made the whole like web graph have this property, so it's not going to be your guy, right? So I so I broke PageRank, right? No. So PageRank realized this, and in fact, sometimes it's kind of someone just didn't put links on their page. But if you're a spammer, then this is actually great, right? I want a random walker to eventually get stuck in a set of nodes, which a set of pages which I think are super interesting, right? So what spammers will try and do is they'll set pages down here, and maybe they'll kind of set these links, and they'll this series of these web pages, right? And they'll get these web pages which are going to have kind of a high score, and then they can sell links to people. It could be back in this part of the graph, right? But you can set up a graph so that all the kind of the random walkers tend to funnel in this way, and then you can sell these. So you can kind of set it up so that random walkers tend to aggregate on certain pages, and then sell a few of these outgoing links, and this will increase would increase the PageRank score. Okay, it would also make things so that it's going to have these. It could be transient if these don't have outgoing links either, but you can kind of like manipulate this graph, okay, by having a bunch of these outgoing edges. All right, so there is a cool fix to this, right, which was realized in the initial PageRank paper, right? So this is an important fix, and it's that I'm going to and so I'm going to do what's called so teleportation. Okay, so you walk around the graph, and then which means 15% of the time, call this a beta parameter. 15% of the time, I'm going to jump to a random page. Okay, so I'm going to define my random walk slightly differently. I'm not always going to follow one of the hyperlinks, but every time I'm at a page and I decide to go out, roughly 1 out of 7 times, I'm going to do a coin flip, and 1 out of 7 times it'll be tails, and that means I jump to a completely random page. What this means is that now every page is linked to every other page, and I now again still don't have cycles. Now it has to be connected. For all the web pages I know about are automatically going to be connected, and it can't have these transient and these absorbing states, right? Because I can always jump out of it, right? And if you're randomly browsing the web, you probably get down some like rabbit hole, and eventually you're like, okay, this is too much, and then you jump to someplace else again, right? So this actually fits with like random surfing might actually do. And 15% I think is the standard number. It could be 10%, something else. But with some probability, you're jumping to like a random page. Okay, and this fixes lots of these issues. If a spammer had this chain of things that was absorbing all this probability, if it's too long, it's going to be jumped out of, right? So it'll probably get jumped out of before it gets down to where it can actually sell these links. These spam farms kind of still do exist, right? So Google will try and kind of find the structure and then downweight the PageRank of it. But it makes it more difficult for them because of these random jumps. Okay, so one more thing before I move on from this picture. Where do these, if I am kind of a spammer, where do these initial links out of the main part of the web graph start from? Right, so where do I get these kind of, there's the regular web that has useful information on it, and then if I'm trying to create these outgoing links into a spam farm so I can then sell the links, like I have to connect to the regular part of the web. I have to get people to start linking to my pages. So how do I do that? Yeah, right. So if you see on these forums or like in like if there's a comments page, right, or you have these fake accounts on Twitter that have like these links in them, right, and it seems like it's a comment and you click on the link and it jumps someplace random. That's what it's doing, right? A lot of these are originating from comment sections and stuff like that, trying to feed this random walk into here, right? So Google knows to kind of jump to stuff in comments of blogs and stuff like that to weight those lower in the random walk. Yeah. So it kind of, and I'll tell a little bit more of another way it can, so it can try and combat this soon as well. Okay, so but to do this random walk, this kind of violates what if I want to actually compute Q star equals P star by 0, right? So I want to compute this kind of this vector, and if I did this by so I want to compute this. So this is essentially the PageRank vector, but this doesn't have the teleportation built into it yet. So trying to compute it by, so one way would be to try and pre-compute. I want to option 1 is going to be run eigs on this matrix P. So P is huge, and so it's millions and billions of web pages. This is actually kind of hard to do. So I don't want to necessarily just run the standard eigenvalue decomposition on P. So option 2 would be to basically I can compute P to the n for large n, and so if I pre-compute this, then for any Q0, I have that Q star equals P, or is approximately, right? So approximately Pn equals Q0, right? So this, maybe you could do this, but there's like this small world phenomena that like this was studied, like if you probably know someone who knows someone who knows someone, after 7 steps they probably know anyone in the world, which would mean that at P7, basically that means in 7 jumps you could get anywhere. So P7 would probably already be very dense, right? So that means it's going to have almost all of the entries filled in. Whereas the regular matrix is actually super sparse, right? Most web pages might have 20 on average outgoing links, right? So even though I have billions of web pages, for each one I need to store just like 20 links. It's not so bad. For the scale of Google, that's nothing. But storing n squared matrix, you know, for Google it'd probably be okay, but for it starts to be much more painful, right? So the option 3, which is the most common thing, is to for I equals 1 to n, do qi plus 1 equals p times qi. Okay, and so I can do this over and over again, and then kind of return q star equals qn, right? So because p is going to be very sparse, this vector matrix multiplication I can do pretty fast. We'll talk Monday about how to scale this up with like MapReduce at extremely large scales, but just now, because I can use this, I preserve the sparsity in here, and this makes it faster. Okay, but now I want to do this instead. I want to have qi plus 1 equals p 1 minus beta plus more space here. So I want to instead do right? So I want to do Q, where Q equals all 1, right? So this basically, or is 1 over n, right? So this is, so if I have this completely n by n matrix Q, that's 1 over n everywhere. So there are n web pages. Let's say m web pages. So an m by m matrix is completely dense, right? When I have these random jumps anywhere, in order to do this, I can no longer have sparse in here. Q is automatically dense. So I can't, so it seems like I can't implement this efficiently anymore. Except I don't need to write it down as the linear algebra, right? I can think like a computer scientist instead and say that this is just a like a random jump to a web page, and so basically I can if it's uniform, I can just pick this. I can implement this as a as basically a random choice. I can take this matrix, compute it, takes this vector, computed by this all 1 over n vector, which is actually just going to be a scaling of this times beta. So I'm just going to scale this qi vector and replace it here. Okay, so actually this computation I can actually do very, very efficiently. Okay, and then this part of it is going to be a sparse matrix vector computation, right? So this is actually 1 minus beta p times qi plus this beta times qi plus 1. No, it's actually, it doesn't, this one doesn't matter what the, this part doesn't matter what this qi vector is. It's just basically a constant. I'm adding to everything. So I'm inflating everything by this amount. Okay, so I can still compute this efficiently using this power method sort of approach. Okay. So this is this is what the PageRank algorithm is, right? So it basically, it runs this kind of power method approach, and probably it sets n equals, I heard sets equal to roughly 50 is usually enough. And if it started with yesterday's PageRank vector as the input, as the initialization, then as we mentioned before, it's going to be, because that's probably similar to what today's PageRank vector is going to be. It probably only needs a few iterations in order to converge from the old one. But if you're starting from scratch, I've heard about 50 iterations is usually enough, unlike the web graph, right? So I run this for 50 steps, and this gives me the PageRank vector, and I use this as part of my scoring function in my index. Okay, so I want to, so there may be 1 or 2 more things I want to talk about today. So I want to mention one other approach against kind of these spamming web pages. And this is an idea called that's called trust rank. And so the main idea is that so there are certain web pages that they trust more. This might be like Wikipedia. Even though it's not perfect, it is actually curated. And so maybe something from a .edu domain. These, again, the university probably has some standards, and if something funny is going on, they'll ask them to take this down, right? So, and so there are probably certain web pages that Google is going to trust more, okay? And so then it can run. Then the idea is to run two versions. So two versions of PageRank. So one is is just like the regular version, where the teleportation is so uniform, right? Where it jumps to just a random web page, and that's what we discussed before. And another is the trust version, where the teleportation step is more likely to jump to a trusted page. Okay, so I clearly I would need more than just Wikipedia and the university domains, but I have to develop some trusted web pages. And the idea is that I'm going to then get these two functions here. So I'm going to get the page rank of a page and the trust rank of a page, and then I can look at something where it can be like the rank of a page minus the trust rank of a page over the rank of a page. Okay, and I can look at this relative difference here. And so if the rank is much larger than the trust rank relative to its score, okay, so then this might be something strange going on. This is more likely to be spam. So larger is more likely spam. If this is small, so the regular page rank and the trust rank is pretty similar, or it's even like negative, then it's probably not spam. It's probably in the domain of some trusted web page if it's negative, and if it's not too different from each other, it's probably okay, right? But if this is drastically different, it's probably, the reason why is probably it's one of these structures that spammers have set up, that it only comes from the comment section or through a bunch of untrusted web pages, and there's a lot of structure which is causing high PageRank score, but it's pretty far away from starting from one of these trust rank scores, from one of these trusted web pages. So you can think of this, what this teleportation is doing is every time I'm effectively starting a random walk, I never walk too far, and I start from one of the trusted web pages. So it's connected. I should still kind of be able to get most anywhere, but if it's very hard to get to a certain set of pages, it had to go through some weird routes. It eventually got to my web page. I linked to a blog post. The comments of the blog post linked to some spam web page that linked to someplace else, which then sold its links. Right? So by then it's taken about 7 steps, and that's about as far as it can go. So it's unlikely to actually make it that far. So those kind of more untrusted web pages are going to have a very large score here, and then I can kind of identify these web pages. Okay, so I can do stuff like this to try and modify what's going on here. Okay, so around 2015, Google, I remember seeing this, I have it in my notes, that I remember seeing Google saying they were going to try and rank web pages based on truth instead of trust. Okay, and this was floated, and then they didn't talk about it anymore, and they don't actually tell you what they actually do. And so my thoughts in 2015 were that why should Google try and curate what's the truth, right? So why should they be like the arbiter of truth? So, you know, there's certain things certain decisions that Google has made as a company which like I disagree with, but there's like a lot of stuff that I also agree with what they've done. I know other companies since then have gone, like Facebook has gone much more backlash about trying to score things based on the truth and not. They have a similar system where they recommend which things go in your feed, and so there was some controversy of how should you try and who's the arbiter of truth here, right? And so my thoughts in 2015 was that the internet would actually do a good job of like self-policing itself, and people would link to things that are truthier. I feel like I was a little bit naive back then, and I think you know, maybe a lot of people like feel this way in retrospect. But as you can see, like probably then in 2015, myself felt Google really had like the upper hand, and these web companies had the upper hand in deciding, understanding how to rank good content on their web pages, right? They had this way of sussing out these spammers that were trying to fool people by not being linked to by trustworthy pages. There are lots of other things. I rarely go past the first page on like Google when I'm looking at the search engine. It works great for that way. There are other places where what's truth, what is being ranked higher in a Facebook feed or on Twitter or other mechanisms, I would say that they're not necessarily the most informative options. Or they're informative, but they may not be kind of a completely unbiased view of the world, and outside actors can gain influence on how things are ranked, right? And so this pendulum has swung back and forth over the years, and I'd say in 2015, I felt like we had that the companies who are providing these tools had a pretty good handle on this. I would say that's less true so like recently, but the pendulum swings back and forth, right? And I don't know what kind of ideas is going to come next year, but it's an interesting space.
So there is a huge chunk of internet called the deep web, which is pretty much arguably bigger than the regular internet we're using.
Yeah.
But that Google search engine does not index those results, does not show them. Is it because those sites block the crawlers so the Google to get to them, or Google itself censors them? Because their traffic is very huge, legitimate traffic. A lot of people visit those sites.
Yeah. So I think it's partly both. So there's some places that will. So you can kind of identify a crawler if you really mean to. Most crawlers you can, and so. So like there's parts of the dark web are like pages inside of Amazon. They have these static pages, but you can only get to them through a link from someplace else, but Amazon can dynamically change them, or the search engine inside of Amazon. So Amazon knows what people are searching for inside of its product page, but Google has a lot more trouble with this. I believe this is kind of part of what is the dark web. It's not these pages that don't necessarily have these static addresses, but are like dynamically defined, and whoever controls that content can control how to access it, right? So that's much harder to crawl and then to build an index on that. Amazon would probably like their products to be indexed on Google, and a bunch of them are. But there are other parts that don't want to be indexed, and there are ways to kind of, you can only access them through some internal way that's not just kind of like vanilla HTML with hyperlinks, right? And so this is, so part of the dark web is that, right? And so like if you're an internal company and you make stuff available to your employees by password, right? That's part of the dark web. You can access it through a web browser in a very similar way, so it's very user-friendly because everyone knows how to use web browsers, but it might be password protected. So then Google's unable to crawl it, and it could be private, so they don't want it to be indexed, right? And so, so probably Google wouldn't have access to it, but they probably build their internal search engine. And there's open source software now that can build search engines. Your computer itself has my laptop has a search engine built into it. I don't think it necessarily uses, I'm not sure if it uses some version of PageRank, but it uses these other tools like cosine similarity. I'm not trying to spam myself with or hopefully not, with stupidly named kind of files. Right, so there's these internal search engines which are built as well. Right, so that is kind of, so there are these pages which aren't in Google, but it doesn't mean that there's not a search engine on them. Yeah. Okay, so I think I'll leave it here. There's a bit more in the notes about personalized PageRank, but and then don't forget your projects are due on Monday, and we'll talk about MapReduce on Monday, which is kind of the system that grew out of Google on how to scale a lot of this stuff up to many, many machines.